What if I told you that the faint glow of static on an old television screen holds the secrets to the birth of the universe? That's right. The cosmic microwave background, or CMB, is not just random noise. It's the oldest light in existence, a snapshot of the universe when it was just a baby, only 380,000 years old. And today, we're diving into 25 mind-blowing facts about this cosmic relic that will change the way you see the night sky forever. From its accidental discovery to the mysteries it still holds about dark matter, dark energy, and the very fabric of space and time, this video is your ultimate guide to understanding the CMB. So buckle up and get ready to explore the universe's oldest selfie, because by the end of this you'll see the cosmos in a whole new light. Let's get started. Now let's zoom in on the very first fact about the cosmic microwave background. It's the oldest light in the universe. Picture this, just 380,000 years after the Big Bang, the universe was a hot, dense soup of particles. But as it expanded and cooled, something incredible happened. Electrons and protons combined to form neutral atoms, and for the first time, light could travel freely through space. This light, now stretched and cooled over billions of years, is what we detect today as the CMB. It's like a cosmic time capsule, giving us a direct glimpse into the universe's infancy. By studying this ancient light, scientists can piece together what the universe was like in its earliest moments, from its temperature to its density. It's not just a relic of the past, it's a key to unlocking the story of how everything we see around us came to be. And that's just the beginning. Next, we'll explore how this light isn't just a distant echo, it's everywhere, filling the entire cosmos. Now, let's take a step further into the cosmic story. The cosmic microwave background isn't just a distant echo from the past, it's everywhere. Imagine standing in a room filled with invisible light, a faint glow that surrounds you no matter where you go. That's what the CMB is like, except it's not confined to a room, it fills the entire universe. This ancient light is so pervasive that if you could see it, you'd notice it coming from every direction, a faint whisper of the universe's earliest moments. But how did we even discover something so universal yet so subtle? The story begins in 1965 with two scientists, Penzias and Robert Wilson. They were working with a large radio antenna in New Jersey, trying to measure signals from space. But no matter where they pointed their antenna, they kept picking up a persistent, mysterious noise. At first, they thought it was interference, maybe from nearby cities or even pigeon droppings on their equipment. They cleaned the antenna, shooed away the pigeons and tried again, but the noise remained. What they didn't realize at the time was that this noise was actually the cosmic microwave background, the faint afterglow of the Big Bang. It wasn't until they connected with a group of physicists, including Robert Dicke, that they understood the significance of their discovery. This accidental finding turned out to be one of the most important breakthroughs in cosmology, earning Penzias and Wilson the Nobel Prize in Physics in 1978. Their discovery didn't just confirm the existence of the CMB, it showed us that this ancient light is everywhere, a constant reminder of the universe's fiery beginnings. And as we'll see next, this light isn't just uniform, it holds tiny clues that reveal even more about the cosmos. Now, let's zoom in a little closer to uncover something truly fascinating about the cosmic microwave background. While it might seem like this ancient light is perfectly smooth and uniform, it's actually not. The CMB has tiny temperature fluctuations, almost like ripples on the surface of a calm lake. These fluctuations, known as anisotropies, are incredibly small, varying by just a fraction of a degree. But don't let their size fool you, they're packed with cosmic significance. These anisotropies are like fingerprints left behind by the early universe. They reveal the seeds of structure that eventually grew into the galaxies, galaxy clusters, and vast cosmic webs we see today. Think of them as tiny bumps in the fabric of space where matter was slightly denser or sparser than average. Over billions of years, gravity amplified these differences, pulling matter together to form the first stars and galaxies. What's truly remarkable is that these fluctuations were predicted by the Big Bang theory long before they were observed. Scientists calculated that if the universe began in a hot, dense state, it would leave behind these subtle imprints. And when satellites like the Cosmic Background Explorer and later the Planck mission mapped the CMB in exquisite detail, they found exactly that, a patchwork of tiny temperature variations that matched the predictions. These anisotropies aren't just random patterns either. They tell us about the universe's composition, its expansion rate, and even the nature of dark matter and dark energy. By studying them, cosmologists can piece together the story of how the universe evolved from a hot, dense soup of particles into the complex, structured cosmos we inhabit today. So, while the CMB might look like a uniform glow at first glance, those tiny fluctuations hold the key to understanding the universe's grand architecture. And as we'll see next, this ancient light doesn't just tell us about the past, it also helps us measure the universe's age and shape. Now, let's take a closer look at how the cosmic microwave background doesn't just tell us about the early universe, it actually confirms one of the most groundbreaking ideas in science, the Big Bang theory. The CMB is like a cosmic smoking gun, providing some of the strongest evidence we have that the universe began in a hot, dense state and has been expanding ever since. When scientists first proposed the Big Bang theory, they predicted that if the universe had indeed started with a massive explosion, it would leave behind a faint afterglow of radiation. This afterglow would cool over billions of years, eventually becoming the microwave background we observe today. And guess what? That's exactly what the CMB is. Its discovery in 1965 by Penzias and Wilson was a game-changer, offering direct proof that the universe had a fiery beginning. But the CMB didn't just support the Big Bang, it also helped settle a major scientific debate. At the time, some scientists favored an alternative idea called the steady-state model, which suggested that the universe had no beginning or end and was constantly creating new matter to maintain its density. However, the CMB's existence and its specific properties, like its temperature and uniformity, were impossible to explain under the steady-state model. The CMB's discovery effectively ruled out this competing theory, solidifying the Big Bang as the leading explanation for the universe's origins. What's even more fascinating is how the CMB's tiny temperature fluctuations, or anisotropies, align perfectly with Big Bang predictions. These fluctuations show that the early universe wasn't perfectly smooth. It had slight variations in density that eventually grew into the galaxies and cosmic structures we see today. This matches the idea that the universe started small and expanded rapidly, cooling as it grew. So the CMB isn't just a relic of the past, it's a powerful piece of evidence that supports the Big Bang theory and helps us understand how the universe evolved. And as we'll see next, this ancient light doesn't just confirm the Big Bang, it also gives us clues about the universe's age and shape, opening up even more cosmic mysteries to explore. Now, let's shift our focus to something that might surprise you: just how cold the cosmic microwave background really is. At a frigid 2.7 Kelvin, or around negative 270.45 degrees Celsius, the CMB is colder than anything you've ever experienced. To put that into perspective, outer space itself is warmer than this ancient light. But why is it so cold, and what does that tell us about the universe's origins? The CMB's temperature is a direct result of the Big Bang. When the universe was born, it was unimaginably hot, a seething cauldron of energy and particles. But as the universe expanded, it cooled down, just like how steam cools as it spreads out. Over billions of years, the heat from that initial explosion has stretched and thinned out, leaving behind the faint afterglow we now detect as the CMB. That 2.7 Kelvin is essentially the leftover heat from the Big Bang, a cosmic fossil that's been chilling ever since. What's fascinating is that this temperature isn't random. It's a precise measurement that aligns perfectly with the predictions of the Big Bang theory. Scientists calculated that if the universe had started in a hot, dense state and expanded over time, the residual radiation would cool to this exact temperature. And when Penzias and Wilson first detected the CMB, they found it matched those predictions almost perfectly. This wasn't just a lucky guess, it was a triumph of scientific reasoning. But here's the kicker: even though the CMB is incredibly cold, it's not uniform. Those tiny temperature fluctuations we mentioned earlier, the anisotropies, are still present, showing that even in this ancient light there are subtle variations. These fluctuations are like cosmic fingerprints, revealing the seeds of structure in the early universe. Without them, galaxies, stars, and planets might never have formed. So, while the CMB's temperature might seem like just a number, it's actually a crucial piece of the puzzle. It's a reminder of the universe's fiery beginnings and a testament to how far we've come in understanding its history. And as we'll see next, this ancient light doesn't just tell us about the past, it also helps us measure the universe's age and shape, unlocking even more secrets of the cosmos. Now, let's take a step back in time, way back to a moment when the universe was just a newborn. Imagine holding a photograph of yourself as a baby, capturing a fleeting moment in your earliest days. The cosmic microwave background is essentially that, but for the entire universe. It's a snapshot, frozen in time, of what the cosmos looked like just 380,000 years after the Big Bang. At that point, the universe was still in its infancy, but it had already undergone a dramatic transformation. Before this era, the universe was so hot and dense that light couldn't travel freely. It was constantly scattered by free electrons. But as the universe expanded and cooled, electrons and protons combined to form neutral atoms, a process known as recombination. This allowed light to finally break free and travel across space. That light, now stretched and cooled over billions of years, is what we detect today as the CMB. Think of it like this: if the universe were a movie, the CMB would be the very first frame we can see. It's not just a blurry image though, it's packed with details. Those tiny temperature fluctuations we've talked about, they're like the brushstrokes in a cosmic painting, revealing the earliest structures in the universe. These fluctuations are the seeds from which galaxies, stars, and eventually planets like ours would grow. What's truly remarkable is how much this snapshot tells us. By studying the CMB, scientists can piece together the conditions of the early universe, its density, temperature, and even the rate at which it was expanding. It's like having a time machine that lets us peer into the universe's first moments. And just like a baby picture, it's a reminder of how far the universe has come since its humble beginnings. So the next time you hear about the CMB, think of it as more than just ancient light. It's a window into the past, a cosmic photograph that captures the universe at its most vulnerable and formative stage. And as we'll see next, this incredible snapshot doesn't just tell us about the universe's infancy, it also holds clues about its composition, helping us understand the building blocks of everything we see today. Now, let's shift our focus to something equally fascinating: what the cosmic microwave background tells us about the universe's ingredients. Just as a recipe reveals the components of a dish, the CMB gives us a detailed breakdown of what makes up the cosmos. And it's not just ordinary matter like stars and planets, it's a mix of some truly mysterious elements. When scientists analyze the CMB, they're able to measure the proportions of different components in the universe. Ordinary matter, the stuff we're made of like atoms and molecules, makes up only about 5% of the universe. That's right, just 5%. The rest is a cosmic cocktail of dark matter and dark energy, two of the most enigmatic substances in existence. Dark matter, which makes up roughly 27% of the universe, doesn't emit, absorb, or reflect light, making it invisible to our telescopes. But its presence is felt through its gravitational effects, which influence the way galaxies and galaxy clusters form. The CMB's temperature fluctuations provide crucial clues about how dark matter is distributed across the cosmos, helping scientists map its invisible web. Then there's dark energy, the most dominant component, accounting for about 68% of the universe. This mysterious force is responsible for the accelerated expansion of the universe, and the CMB offers insights into how it behaves. By studying the patterns in the CMB, scientists can trace the history of the universe's expansion and better understand the role dark energy plays in shaping its future. What's truly remarkable is how the CMB acts as a cosmic scale, weighing the universe's components with incredible precision. It's like having a universal recipe book where each ingredient, ordinary matter, dark matter, and dark energy, has its own unique role in the grand cosmic dish. And as we continue to study the CMB, we're not just learning about what the universe is made of, we're uncovering the very blueprint of its existence. So the next time you think about the universe, remember that it's not just stars and galaxies out there. The CMB reveals a much richer, more complex picture, one where dark matter and dark energy play starring roles in the cosmic story. And as we'll see next, this ancient light doesn't just tell us about the universe's composition, it also holds secrets about its earliest moments, including the rapid expansion known as cosmic inflation. Now, let's turn our attention to another fascinating aspect of the cosmic microwave background, its polarization. Just as sunlight reflecting off a lake creates patterns of light, the CMB carries a subtle imprint of polarization, a property that reveals even more about the universe's earliest moments. This polarization isn't just a random feature, it's a treasure trove of information about the universe's infancy, including the dramatic period known as cosmic inflation. Polarization occurs when light waves vibrate in a specific direction, and in the case of the CMB, this happens because of the way light interacted with matter in the early universe. As the universe cooled and electrons combined with protons to form neutral atoms during the recombination era, photons were finally able to travel freely. But before this moment, those photons were constantly scattering off electrons, creating a unique pattern of polarization in the CMB. This pattern is like a fingerprint, preserving details about the universe's conditions just moments after the Big Bang. One of the most exciting discoveries tied to CMB polarization is its connection to cosmic inflation. The theory that the universe underwent an incredibly rapid expansion in the first fraction of a second after the Big Bang. During this explosive growth, tiny quantum fluctuations were stretched to cosmic scales, seeding the structures we see today like galaxies and galaxy clusters. These fluctuations also left their mark on the CMB's polarization, creating a specific type of pattern known as B-mode polarization. Detecting these patterns is like finding a cosmic time capsule, offering direct evidence of inflation and helping scientists piece together how the universe began. But the story doesn't end there. The CMB's polarization also provides clues about the universe's first particles, including cosmic neutrinos. These ghostly particles, which barely interact with matter, were abundant in the early universe and influenced the way light polarized. By studying these subtle effects, scientists can learn more about the behavior of neutrinos and their role in shaping the cosmos. In essence, the polarization of the CMB is like a cosmic detective, uncovering secrets about the universe's earliest moments. It's not just a snapshot of the past, it's a dynamic record of the forces and particles that set the stage for everything we see today. And as we'll explore next, this ancient light doesn't just tell us about the universe's beginnings, it also helps us measure its age, offering a window into the timeline of cosmic history. Now, let's shift our focus to how the cosmic microwave background serves as a cosmic clock, helping scientists determine the age of the universe. The the CMB isn't just a relic of the past, it's a precise tool that allows us to peer back in time and measure how long the universe has existed. By analyzing the CMB's temperature fluctuations and the patterns of its light, researchers have been able to calculate the universe's age with remarkable accuracy, currently estimated at around 13.8 billion years. Here's how it works. The CMB provides a snapshot of the universe when it was just 380,000 years old, capturing the conditions of that moment in exquisite detail. By studying the distribution of temperature variations, those tiny anisotropies we discussed earlier, scientists can trace the expansion rate of the universe over time. This expansion rate, known as the Hubble constant, is a key piece of the puzzle. When combined with measurements of the universe's density and composition derived from the CMB, it allows researchers to calculate how long it took for the universe to grow from its fiery beginnings to the vast cosmos we see today. One of the most fascinating aspects of this process is how the CMB acts as a calibration tool for other methods of measuring the universe's age. For example, observations of distant supernova and the distribution of galaxies also provide clues about cosmic expansion. But the CMB offers a unique baseline, a reference point that helps refine these measurements and resolve discrepancies. It's like having a master key that unlocks multiple doors, each leading to a deeper understanding of the universe's timeline. The precision of this age estimate is truly astounding. 13.8 billion years might sound like an abstract number, but it represents the culmination of countless observations, calculations, and cross-checks. It's a testament to the power of the CMB as a scientific tool and a reminder of how far we've come in unraveling the mysteries of the cosmos. And as we'll see next, this ancient light doesn't just tell us about the universe's age, it also offers insights into its geometry, revealing whether the cosmos is flat, open, or closed. Now, let's take a closer look at how the cosmic microwave background opens a window into one of the most mind-bending ideas in cosmology, cosmic inflation. This theory suggests that in the first fraction of a second after the Big Bang, the universe underwent an unimaginably rapid expansion, stretching from something smaller than an atom to nearly the size of a grapefruit in less than a blink of an eye. And the CMB, it's the key piece of evidence that supports this extraordinary idea. When we examine the CMB's temperature fluctuations, we're not just seeing random variations, we're looking at the fingerprints of cosmic inflation. These tiny anisotropies, or differences in temperature, are incredibly uniform across the sky, but they also contain subtle patterns that match what scientists would expect if the universe had expanded exponentially in its earliest moments. It's like finding a perfectly preserved fossil that tells us exactly how the universe grew in its infancy. But how does inflation explain these patterns? During that rapid expansion, quantum fluctuations, tiny ripples in the fabric of space-time, were stretched to cosmic scales. These ripples became the seeds for the temperature variations we see in the CMB, which later grew into the galaxies, stars, and planets we know today. Without inflation, the universe wouldn't have the large-scale structure we observe, and the CMB wouldn't look the way it does. What's even more fascinating is that the CMB's polarization, the way its light waves are oriented, also supports the inflation theory. Certain patterns in this polarization, known as B-mode polarization, are thought to be caused by gravitational waves generated during inflation. While detecting these signals has been challenging, their discovery would be a smoking gun for inflation, confirming that the universe really did undergo this explosive growth spurt. The CMB doesn't just tell us about the universe's age or composition, it's a time machine that takes us back to the very first moments of existence. By studying it, we're piecing together the story of how everything began, and cosmic inflation is one of the most thrilling chapters in that story. And as we'll see next, this ancient light doesn't just reveal the universe's past, it also helps us understand its shape, answering the question of whether the cosmos is flat, open, or closed. Now, let's shift our focus to something that might surprise you. The cosmic microwave background is completely invisible to the naked eye. That's right, despite being the oldest light in the universe, you can't see it when you look up at the night sky. But why is that? The answer lies in the nature of the CMB itself. The CMB is made up of microwave radiation, which falls outside the range of light that human eyes can detect. Our eyes are designed to see visible light, which is just a tiny sliver of the electromagnetic spectrum. Microwaves, on the other hand, have much longer wavelengths than visible light, making them impossible for us to perceive without the help of specialized tools. This is where instruments like radio telescopes come into play. These devices are specifically designed to detect microwave radiation, allowing scientists to see the CMB in a way that our eyes never could. Radio telescopes capture the faint signals of the CMB and translate them into data that researchers can analyze. Without these advanced instruments, the CMB would remain hidden from us, a cosmic secret locked away in the invisible spectrum of light. Interestingly, the fact that the CMB is invisible to us also highlights just how much of the universe lies beyond our natural senses. It's a reminder that the cosmos is full of phenomena that require technology to uncover, pushing the boundaries of what we can observe and understand. And as we'll explore next, this ancient light doesn't just reveal the universe's hidden past, it also helps us map its large-scale structure, giving us a clearer picture of how everything fits together. Now, let's take a step back in time, way back to an era that shaped the very fabric of our universe. The cosmic microwave background isn't just ancient light. It's a direct relic of a pivotal moment in cosmic history known as the recombination era. This was a time roughly 380,000 years after the Big Bang, when the universe underwent a dramatic transformation. Before this era, the universe was a hot, dense soup of charged particles, protons and electrons swimming in a sea of intense radiation. Light couldn't travel far without bumping into these charged particles, making the universe opaque like a thick cosmic fog. But as the universe expanded and cooled, something extraordinary happened. Protons and electrons began to combine, forming neutral hydrogen atoms. This process, called recombination, fundamentally changed the universe's structure. With the formation of neutral atoms, the fog lifted. Light, which had been trapped and scattered by the charged particles, was finally free to travel unimpeded. This newly liberated light is what we now detect as the cosmic microwave background. It's essentially the afterglow of that momentous event, a snapshot of the universe as it transitioned from a chaotic, opaque state to one where light could stream freely across the cosmos. The recombination era didn't just create the CMB, it also set the stage for the universe we see today. By allowing light to travel freely, it enabled the formation of the first structures that would eventually grow into galaxies, stars, and planets. And because the CMB captures this critical moment, it serves as a time capsule, preserving the conditions of the early universe for us to study billions of years later. As we continue to decode the secrets of the CMB, we're not just looking at ancient light, we're peering into the very moment when the universe became transparent, setting the foundation for everything that followed. And speaking of foundations, the CMB doesn't just tell us about the past, it also helps us map the universe's large-scale structure, a topic we'll explore next. Now, let's shift our focus to one of the most profound ways the cosmic microwave background has shaped our understanding of the universe, by serving as a cosmic laboratory for testing Einstein's theory of general relativity. This groundbreaking theory, which describes how gravity works on the largest scales, has been a cornerstone of modern physics. But how does the CMB fit into this? The CMB offers a unique testing ground because it captures the universe's conditions at a time when gravity was the dominant force shaping its evolution. The tiny temperature fluctuations, or anisotropies, in the CMB are like fingerprints left behind by the gravitational interactions of matter in the early universe. These patterns allow scientists to test whether general relativity accurately predicts how matter and energy behaved on cosmic scales billions of years ago. One of the key predictions of general relativity is how massive objects like galaxy clusters bend the path of light, a phenomenon known as gravitational lensing. The CMB's light has traveled across the universe for over 13 billion years, and during that journey, it has been subtly distorted by the gravitational pull of massive structures. By studying these distortions, researchers can verify whether general relativity holds true even on the vast scales of the cosmos. But the CMB doesn't just confirm what we already know, it also challenges us to refine our understanding. For instance, some observations of the CMB have hinted at subtle discrepancies that could point to new physics beyond general relativity. These anomalies, while still under investigation, suggest that there might be more to gravity than Einstein's equations currently describe. In essence, the CMB acts as a cosmic proving ground, allowing us to test one of the most fundamental theories of physics in ways that would be impossible in a laboratory. It's a reminder that the universe itself is the ultimate experiment, and the CMB is one of our most powerful tools for uncovering its deepest secrets. As we continue to explore the CMB's role in testing general relativity, we're not just validating a century-old theory, we're also pushing the boundaries of what we know about gravity, space, and time. And with that, let's turn our attention to how the CMB maps the universe's large-scale structure, revealing the cosmic web that connects galaxies across the cosmos. Now, let's take a closer look at how the cosmic microwave background serves as a cosmic map, revealing the universe's large-scale structure. The tiny temperature fluctuations, or anisotropies, in the CMB are more than just random variations. They're a blueprint of how matter was distributed in the early universe. These patterns are like a snapshot of the universe's infancy, capturing the seeds of what would eventually grow into galaxies, galaxy clusters, and the vast cosmic web we see today. When the universe was just 380,000 years old, the distribution of matter was imprinted onto the CMB. Denser regions where matter was slightly more concentrated appear as slightly warmer spots in the CMB, while less dense regions show up as cooler areas. These fluctuations might seem small, but they hold the key to understanding how the universe evolved over billions of years. Over time, gravity took hold of these initial irregularities, pulling matter together to form the first stars, galaxies, and eventually the massive structures we observe today. The CMB's anisotropies act as a guide, helping scientists trace the growth of cosmic structures from their humble beginnings to the sprawling networks of galaxies and clusters that span the cosmos. What's truly remarkable is how well the CMB's map aligns with our observations of the universe today. By comparing the CMB's patterns with modern surveys of galaxy distributions, researchers can test their models of cosmic evolution and refine our understanding of how the universe grew from its early state to the complex, interconnected web we see now. This cosmic map doesn't just tell us about the past, it also provides clues about the universe's future. By studying how matter was distributed in the early universe, scientists can make predictions about how structures will continue to evolve, offering insights into the fate of galaxies and the large-scale structure of the cosmos. As we delve deeper into the CMB's role as a cosmic map, we're not just uncovering the history of the universe, we're also gaining a clearer picture of its present and future. And with that, let's explore how the CMB helps us measure one of the most fundamental constants in cosmology, the Hubble constant, which tells us how fast the universe is expanding. Now, shifting our focus to another groundbreaking role of the cosmic microwave background, let's explore how it helps us measure the Hubble constant, a key piece of the puzzle in understanding the universe's expansion. The Hubble constant tells us how fast the universe is growing, and the CMB provides a unique way to calculate this rate with remarkable precision. When scientists study the CMB, they're not just looking at a static image of the early universe, they're analyzing a dynamic record of cosmic evolution. The tiny temperature fluctuations in the CMB, those anisotropies we've discussed, contain information about how quickly the universe was expanding when the CMB was formed. By measuring the size and distribution of these fluctuations, researchers can infer the rate of expansion at that time. But how does this connect to the Hubble constant? The key lies in the relationship between the CMB and the universe's overall geometry. The CMB's patterns reveal the universe's curvature, which in turn influences how fast it expands. By combining this data with observations of distant galaxies and supernova, scientists can calculate the Hubble constant with incredible accuracy. Interestingly, the CMB's measurement of the Hubble constant doesn't always align perfectly with other methods, like those using nearby galaxies. This discrepancy, known as the Hubble tension, has sparked intense debate among cosmologists. Some suggest it could point to new physics, such as unknown forms of dark energy or modifications to our understanding of gravity. Others believe it might be due to subtle errors in measurements. Either way, the CMB remains a critical tool in this ongoing investigation. What makes the CMB so powerful in this context is its ability to provide a snapshot of the universe at a specific moment in time, 380,000 years after the Big Bang. By comparing this ancient data with modern observations, scientists can trace the universe's expansion over billions of years, refining their estimates of the Hubble constant and deepening our understanding of cosmic evolution. As we continue to study the CMB, it's clear that this ancient light isn't just a relic of the past, it's a vital tool for unlocking the mysteries of the universe's expansion. And with that, let's turn our attention to how the CMB is affected by gravitational lensing, a phenomenon that bends its light and reveals even more about the cosmos. Now, let's dive into another fascinating aspect of the cosmic microwave background, how it interacts with the immense gravitational pull of massive objects in the universe. This phenomenon, known as gravitational lensing, occurs when the light from the CMB passes near galaxy clusters or other dense structures. These massive objects warp the fabric of space-time, bending the CMB's light as it travels toward us. This bending creates subtle distortions in the CMB's patterns, almost like looking at the universe through a cosmic magnifying glass. These distortions aren't just random. They carry valuable information about the distribution of matter in the universe, particularly dark matter. Since dark matter doesn't emit or absorb light, it's invisible to traditional telescopes, but its gravitational effects are unmistakable, and the CMB provides a unique way to map its presence. When scientists analyze these lensing effects, they can trace the invisible web of dark matter that stretches across the cosmos. This web acts as a scaffold for the formation of galaxies and galaxy clusters, shaping the large-scale structure of the universe. By studying how the CMB's light is bent, researchers can measure the amount and distribution of dark matter with remarkable precision. What's truly remarkable is that gravitational lensing doesn't just reveal dark matter. It also helps us understand how the universe has evolved over billions of years. The distortions in the CMB's light provide a snapshot of how matter, both visible and dark, has clumped together over time. This information is crucial for testing our models of cosmic evolution and refining our understanding of the universe's composition. So, while the CMB itself is a relic of the early universe, its interaction with gravitational lensing offers a window into the hidden forces shaping the cosmos today. And as we continue to study these subtle distortions, we uncover more clues about the mysterious nature of dark matter and its role in the grand tapestry of the universe. With that in mind, let's shift our focus to another intriguing connection: how the CMB provides evidence for the existence of cosmic neutrinos, particles that were abundant in the early universe and continue to influence its evolution. Now, let's turn our attention to another fascinating piece of the cosmic puzzle: how the cosmic microwave background sheds light on the existence of cosmic neutrinos. These elusive particles, often called ghost particles, are incredibly lightweight and barely interact with matter, making them nearly impossible to detect directly. Yet, they played a crucial role in the early universe, and the CMB holds clues to their presence. When the universe was just a fraction of a second old, cosmic neutrinos were everywhere, zipping through space at nearly the speed of light. As the universe expanded and cooled, these neutrinos decoupled from matter, meaning they stopped interacting with other particles and began traveling freely. This decoupling happened even earlier than the release of the CMB itself, making neutrinos some of the oldest relics of the Big Bang. So, how does the CMB help us detect these ghostly particles? The answer lies in the subtle imprints they left behind. As neutrinos streamed through the early universe, their presence influenced the distribution of matter and the way light traveled. These effects are encoded in the tiny temperature fluctuations of the CMB, which scientists can analyze to infer the existence and properties of cosmic neutrinos. One of the most remarkable findings is that the CMB provides evidence for the number of neutrino species in the universe. By studying the patterns in the CMB, researchers have confirmed that there are 3 types of neutrinos, matching what particle physics predicts. This alignment between cosmology and particle physics is a stunning example of how the CMB bridges the gap between the largest and smallest scales of the universe. But the story doesn't end there. Cosmic neutrinos also played a role in shaping the universe's large-scale structure. Their rapid movement in the early universe created a kind of drag on the growth of matter, slowing down the formation of galaxies and clusters. This effect is subtly recorded in the CMB's anisotropies, giving us a glimpse into how neutrinos influenced cosmic evolution. What's truly mind-blowing is that these neutrinos are still around today, flowing through space and even through you in vast numbers. Yet, it's the CMB that allows us to see their impact, even though we can't detect them directly. By studying these ancient particles through the lens of the CMB, we gain a deeper understanding of the universe's earliest moments and the forces that shaped its destiny. With this in mind, let's explore another intriguing aspect of the CMB: how it encodes the sound waves of the early universe, offering a unique auditory glimpse into the cosmos's infancy. Now, let's dive into something truly extraordinary: how the cosmic microwave background captures the sound waves of the early universe. Imagine the cosmos as a vast, echoing chamber, filled with ripples of energy that shaped everything we see today. These ripples, or sound waves, were created in the first moments after the Big Bang, when the universe was a hot, dense soup of particles and radiation. As the universe expanded, these sound waves traveled through the primordial plasma, compressing and stretching matter in their wake. Think of it like dropping a pebble into a pond. The ripples spread out, creating patterns on the surface. In the early universe, these ripples weren't just visual, they were acoustic, leaving behind a kind of cosmic symphony. When the universe cooled enough for atoms to form, around 380,000 years after the Big Bang, light was finally able to travel freely. This moment is what we see in the CMB, a snapshot of those ancient sound waves frozen in time. The temperature fluctuations in the CMB aren't random. They're the imprints of those early acoustic waves, revealing how matter was distributed across the cosmos. Scientists call these patterns Baryon acoustic oscillations, and they're like the fingerprints of the universe's first sounds. By studying these oscillations, researchers can trace how matter clumped together to form galaxies, galaxy clusters, and even the vast cosmic web we observe today. It's as if the CMB is a cosmic record player, letting us listen to the echoes of the universe's infancy. What's even more fascinating is that these sound waves weren't just random noise, they followed precise mathematical patterns. The spacing between the ripples in the CMB corresponds to the distance sound could travel in the early universe before it cooled. This distance acts as a standard ruler, allowing scientists to measure the scale of the universe with incredible precision. So, while we can't literally hear the CMB, its patterns tell us a story about the universe's first sounds. a story that continues to shape our understanding of cosmic evolution. And with that, let's move on to another captivating aspect of the CMB, how it challenges alternative theories of the universe, opening doors to even more cosmic mysteries. Now, let's shift our focus to how the cosmic microwave background serves as a powerful test for alternative theories about the universe. While the Big Bang theory is the most widely accepted explanation for the universe's origins, it's not the only idea out there. Some scientists have proposed alternative models like cyclic universes or multiverse scenarios, where our universe is just one of many. But here's the thing, the CMB doesn't just support the Big Bang theory, it also puts these alternative ideas to the test. Take cyclic models, for example. These theories suggest that the universe goes through endless cycles of expansion and contraction like a cosmic heartbeat. While this idea is fascinating, the CMB's precise temperature fluctuations and the patterns of baryon acoustic oscillations we discussed earlier don't quite align with what cyclic models predict. The CMB's data strongly favors a universe that began with a single, explosive event, the Big Bang, rather than one that's been cycling through endless rebirths. Then there's the multiverse hypothesis, which proposes that our universe is just one of countless others, each with its own unique set of physical laws. While this idea is intriguing, the CMB doesn't provide direct evidence for it. In fact, the uniformity and specific features of the CMB suggest that our universe had a very specific set of initial conditions, which are hard to reconcile with the idea of an infinite number of random universes. What makes the CMB such a powerful tool is its ability to provide concrete data that either supports or challenges these theories. It's like a cosmic detective, sifting through the evidence to help us separate fact from speculation. And while alternative cosmologies are still worth exploring, the CMB has so far stood as a robust pillar supporting the Big Bang model, while raising tough questions for other ideas. This doesn't mean alternative theories are completely ruled out. Science is always evolving, and new discoveries could shift our understanding. But for now, the CMB remains one of the most compelling pieces of evidence we have for the Big Bang, while also serving as a litmus test for other cosmic ideas. And with that, let's turn our attention to another fascinating role the CMB plays, helping us unravel the mysteries of dark energy, the force driving the universe's accelerated expansion. Now, let's dive into one of the most intriguing mysteries of the cosmos: dark energy. This invisible force is responsible for the universe's accelerated expansion, and believe it or not, the cosmic microwave background plays a key role in helping us understand it. The CMB provides a unique window into the universe's expansion history. By studying the patterns and distribution of temperature fluctuations in the CMB, scientists can trace how the universe has grown over billions of years. These fluctuations act like cosmic breadcrumbs, revealing how matter and energy have evolved since the Big Bang. One of the most surprising discoveries in modern cosmology is that the universe isn't just expanding, it's doing so at an ever-increasing rate. This acceleration is driven by dark energy, a mysterious force that makes up about 68% of the universe's total energy content. But here's the catch: we don't know what dark energy actually is. It doesn't emit light, absorb light, or interact with matter in any way we can directly detect. So how do we study something so elusive? This is where the CMB comes in. By analyzing the CMB's large-scale structure, scientists can measure the universe's expansion rate at different points in time. These measurements help us understand how dark energy has influenced the cosmos over billions of years. For example, the CMB's anisotropies, those tiny temperature variations we've talked about, allow researchers to calculate the universe's geometry and the amount of dark energy present. Interestingly, the CMB also helps us test different theories about dark energy. Some models suggest that dark energy is a constant force, represented by Einstein's cosmological constant. Others propose that it changes over time, growing stronger or weaker as the universe evolves. The CMB's precise measurements provide critical data to evaluate these ideas, helping scientists refine their understanding of this enigmatic force. What's truly remarkable is that the CMB doesn't just tell us about the universe's past, it also gives us clues about its future. By understanding dark energy's role in cosmic expansion, we can make predictions about how the universe will evolve billions of years from now. Will it continue to expand forever, or could dark energy eventually lead to a dramatic cosmic event like the Big Rip? The CMB's insights are helping us explore these profound questions. So, while dark energy remains one of the greatest puzzles in science, the CMB is an invaluable tool in our quest to unravel its secrets. It's a reminder that even the faintest glow from the early universe can illuminate some of the deepest mysteries of existence. And with that, let's move on to another fascinating aspect of the CMB, its role as a cosmic thermometer, revealing the universe's thermal history. Now, let's shift our focus to something equally fascinating: how the cosmic microwave background acts as a cosmic thermometer, offering us a glimpse into the universe's thermal history. You might be wondering, how can something as cold as the CMB, with its temperature of just 2.7 Kelvin, tell us anything about heat? Well, it's all about context. The CMB's temperature is a direct remnant of the universe's fiery beginnings. After the Big Bang, the universe was an incredibly hot and dense soup of particles and energy. As it expanded and cooled, it reached a point around 380,000 years after the Big Bang, where electrons and protons combined to form neutral atoms. This moment, known as recombination, allowed light to travel freely for the first time, creating the CMB. The temperature of this light, 2.7 Kelvin, is essentially the universe's way of preserving a snapshot of its thermal state at that time. But the CMB doesn't just tell us about the universe's temperature at one moment in history. It also reveals how the universe has cooled over time. By studying the CMB's temperature, scientists can trace the thermal evolution of the cosmos, from its scorching origins to its current, much cooler state. This cooling process is a direct result of the universe's expansion. As space stretches, the energy within it spreads out, causing temperatures to drop. The CMB's temperature is a testament to this ongoing cosmic cooling. What's even more intriguing is that the CMB's temperature isn't perfectly uniform. Those tiny fluctuations we've talked about, the anisotropies, aren't just random. They're like cosmic fingerprints, encoding information about the density and temperature variations in the early universe. These fluctuations tell us how matter and energy were distributed, giving us clues about the processes that shaped the universe's structure. For example, regions that were slightly hotter in the early universe eventually became the seeds for galaxies and galaxy clusters, while cooler regions evolved into the vast cosmic voids we see today. The CMB's temperature also helps us test our understanding of fundamental physics. For instance, it provides a way to verify the predictions of the Big Bang theory. If the universe had a different origin story, the CMB's temperature and its fluctuations wouldn't match what we observe. But so far, the CMB's measurements align beautifully with our current models, reinforcing our confidence in the Big Bang as the starting point of everything. In a way, the CMB is like a time capsule, preserving the thermal history of the universe in its faint glow. It's a reminder that even the coldest light can carry the warmth of cosmic memory, helping us piece together the story of how our universe came to be. And with that, let's turn our attention to another remarkable feature of the CMB: its ability to reveal the universe's geometry, a key piece of the cosmic puzzle. Now, let's take a closer look at how the cosmic microwave background serves as a powerful tool for uncovering the universe's geometry. You might be wondering, how can light from the early universe tell us about the shape of space itself? The answer lies in the subtle patterns hidden within the CMB's temperature fluctuations. The Big Bang theory predicts that the universe should have a specific geometry: flat, open, or closed. A flat universe means that parallel lines will never meet, and the angles of a triangle add up to 180 degrees, just like in the geometry we learn in school. An open universe would curve outward like a saddle, while a closed universe would curve inward like a sphere. So how do we know which one describes our cosmos? This is where the CMB comes in. The tiny temperature variations in the CMB, those anisotropies we've discussed, act like a cosmic ruler. By measuring the size and distribution of these fluctuations, scientists can determine the universe's geometry. If the universe were open or closed, the patterns in the CMB would appear distorted, like looking at a reflection in a funhouse mirror. But what we observe is a remarkably consistent and uniform pattern, one that aligns perfectly with the predictions of a flat universe. This discovery is a major triumph for the Big Bang theory. It not only confirms that the universe is flat, but also provides critical insights into the total amount of matter and energy in the cosmos. A flat universe implies a precise balance between matter, and dark energy, a balance that has shaped the evolution of everything we see today. But the CMB doesn't just stop at telling us the universe is flat. It also helps us understand why. The theory of cosmic inflation, which suggests that the universe underwent an incredibly rapid expansion in its earliest moments, predicts a flat geometry as a natural outcome. The CMB's measurements provide strong support for this idea, offering a glimpse into the universe's first moments and the forces that set its shape in motion. In essence, the CMB is like a cosmic blueprint, revealing the geometry of the universe with incredible precision. It's a reminder that even the faintest light can illuminate the grandest truths about our cosmos. And with that, let's move on to explore how the CMB acts as a time capsule, preserving the universe's earliest moments for us to study billions of years later. Now, let's shift our focus to something truly remarkable: how the cosmic microwave background acts as a time capsule, preserving the universe's earliest moments for us to study billions of years later. Imagine holding a photograph taken just moments after the Big Bang. That's essentially what the CMB is: a snapshot frozen in time, capturing the universe when it was a mere 380,000 years old. This ancient light carries with it a wealth of information about the conditions of the early universe. The temperature fluctuations, or anisotropies, we've talked about earlier, aren't just random patterns. They're like cosmic fingerprints, encoding details about the density, pressure, and even the motion of matter in those first moments. These tiny ripples in the CMB are the seeds from which galaxies, stars, and eventually planets like ours would grow. But how does the CMB preserve this information so perfectly? The answer lies in the recombination era, a pivotal moment in cosmic history. Before this time, the universe was a hot, dense soup of particles, with light constantly scattering off electrons, making it impossible for photons to travel freely. But as the universe expanded and cooled, electrons and protons combined to form neutral atoms, allowing light to break free and travel across space. This first light is what we now detect as the CMB, carrying with it the imprint of the universe's infancy. What's truly astounding is how much we can learn from this ancient light. By analyzing the CMB, scientists can reconstruct the universe's temperature, density, and even the speed of sound in the early cosmos. It's like having a detailed record of the universe's first moments, written in the language of light, and here's where it gets even more fascinating. The CMB doesn't just tell us about the past, it also gives us clues about the universe's future. The patterns we see in the CMB are directly linked to the distribution of matter and energy that would shape the cosmos over billions of years. In a way, the CMB is both a time capsule and a cosmic crystal ball, offering insights into where the universe came from and where it's headed. So, the next time you hear about the cosmic microwave background, remember, it's not just a faint glow in the sky. It's a treasure trove of information, a window into the universe's earliest moments, and a testament to the incredible power of light to carry stories across billions of years. With that in mind, let's turn our attention to the cosmic mysteries that the CMB still holds and how it continues to challenge our understanding of the universe. Now, let's dive into one of the most intriguing aspects of the cosmic microwave background, its role as a source of cosmic mysteries. While the CMB has provided us with an incredible wealth of knowledge about the universe, it has also left us with some profound questions that continue to puzzle scientists. One of the biggest mysteries tied to the CMB is the nature of dark matter. We know dark matter exists because of its gravitational effects on galaxies and galaxy clusters, but we still don't know what it's made of. The CMB offers clues as its anisotropies, those tiny temperature fluctuations, reveal how dark matter influenced the distribution of matter in the early universe. Yet, despite these clues, dark matter remains elusive, and its true identity is one of the greatest unsolved puzzles in cosmology. Another mystery lies in the cause of cosmic inflation. The CMB provides strong evidence that the universe underwent a rapid expansion just moments after the Big Bang, but we don't fully understand what triggered this inflation or why it stopped. The patterns in the CMB's polarization hint at the energy scales involved, but the exact mechanism behind this explosive growth remains unknown. It's like having a snapshot of the aftermath of a cosmic event without knowing what caused it in the first place. And then there's the question of dark energy. The CMB helps us measure the universe's expansion rate, which led to the discovery that this expansion is accelerating. Dark energy is thought to be the driving force behind this acceleration, but its nature is still a mystery. Is it a property of space itself, or is it something entirely different? The CMB gives us hints, but the answers remain just out of reach. These unresolved questions remind us that the CMB is not just a relic of the past, it's a gateway to the unknown. Every time we uncover a new detail about the CMB, it seems to open up even more questions about the universe, and that's what makes it so exciting. The CMB isn't just a map of where we've been, it's a guide to the mysteries we have yet to solve. As we continue to study the CMB with ever more advanced tools, who knows what secrets we might uncover next? Perhaps the answers to these cosmic mysteries are hidden in the faint glow of this ancient light, waiting for us to decode them. And with that thought, let's move on to our final point: how the CMB is not just a relic of the past, but a gateway to new discoveries that could reshape our understanding of the cosmos. As we wrap up our journey through the mysteries of the cosmic microwave background, it's impossible not to marvel at how this ancient light continues to guide us toward new discoveries. The CMB isn't just a relic of the past, it's a living, breathing map of the cosmos, constantly revealing new layers of understanding about the universe's origins and evolution. Every time we peer into the faint glow of the CMB, we're essentially looking back in time, uncovering clues about the universe's earliest moments. But it's not just about the past. The CMB also holds the key to understanding the future of our universe. By studying its patterns, scientists can make predictions about how the universe will continue to expand and evolve, offering us a glimpse into the ultimate fate of everything we know. What's truly remarkable is how the CMB keeps surprising us. With each new observation, whether from ground-based telescopes or space missions like the Planck satellite, we uncover details that challenge our assumptions and push the boundaries of our knowledge. For instance, recent studies of the CMB's polarization have hinted at the possibility of gravitational waves from the early universe, which could provide direct evidence of cosmic inflation. These findings could revolutionize our understanding of the Big Bang itself. And let's not forget the role of technology in this ongoing quest. As our instruments become more sensitive and our methods more sophisticated, we're able to extract even more information from the CMB's subtle signals. It's like upgrading from an old, blurry photograph to a high-resolution image. Each new level of detail brings us closer to solving the universe's greatest mysteries. So, what's next for the CMB? The possibilities are endless. future missions and experiments could reveal even more about dark matter, dark energy, and the fundamental forces that shape the cosmos. The CMB is a treasure trove of information, and we've only just begun to scratch the surface. In the end, the cosmic microwave background is more than just a scientific tool. It's a testament to humanity's curiosity and determination to understand the universe. It reminds us that the cosmos is full of secrets waiting to be uncovered, and that every discovery brings us one step closer to answering the biggest questions of all. Where did we come from? And where are we going? With that, we've reached the end of our list, but certainly not the end of the story. The CMB will continue to be a source of wonder and inspiration for generations to come, guiding us as we explore the vast, mysterious universe we call home. Thanks for joining me on this cosmic journey. Don't forget to like, subscribe, and hit the notification bell for more space mysteries. From the oldest light in the universe to the secrets of cosmic inflation, the cosmic microwave background has taken us on an incredible journey through space and time. We've explored how this faint glow, dating back to just 380,000 years after the Big Bang, serves as a cosmic time capsule, preserving the universe's earliest moments. We've seen how its tiny temperature fluctuations reveal the seeds of galaxies, how it confirms the Big Bang theory, and how it helps us measure the universe's age and composition. The CMB isn't just a scientific tool, it's a window into the very fabric of the cosmos. It's shown us the universe's flat geometry, helped us map dark matter and dark energy, and even hinted at the existence of cosmic neutrinos. It's a testament to the power of human curiosity and innovation. From the accidental discovery by Penzias and Wilson to the cutting-edge missions like Planck that continue to push the boundaries of our understanding. But perhaps the most exciting part is that the story of the CMB is far from over. With every new discovery, we're reminded that the universe is full of mysteries waiting to be solved. The CMB will continue to guide us, offering clues about the universe's origins, its evolution, and its ultimate fate. So, what do you think? Did any of these facts about the cosmic microwave background surprise you? Let me know in the comments below. I'd love to hear your thoughts. And if you enjoyed this cosmic journey, don't forget to hit that like button, subscribe to the channel, and ring the notification bell so you never miss out on more space mysteries. Until next time, keep looking up. The universe has so much more to show us.